Joint work with Gene Smith, who was my supervisor at Warwick during my PhD, and some other people, Martin Barons and Christian Gergen, who are at Warwick, and Eva Ricomagno is at the University of Genoa. What I will talk about is the need of integrating probabilistic outputs from a suite of models and the challenges that this sort of integration might lead to, and also why is it reasonable to do that. So where I will start from is by saying that the Bayesian framework of probabilistic reasoning has been defined for single users, and by modeling probabilistically, you have a coherent framework, and because you know what to do by following the rules of probability. And as we have seen all throughout this conference, you have like a fast framework to do inference and whatever you want to do with your model. But in some applications, the complexity of the domain you're trying to model means that one model will not be enough, but actually what you will try to do is to connect different suite of models together into a unique model. And people who will make decisions based on these models will not be individuals, but decision centers. And what you will have is like different group of experts, each group informing one of the models of this network. And in the next slide, I will talk about an application, and you can see why you might want to do that. So in these types of domains, you move from a single user context to a plural environment where you have very different variables, very different group of people, and you want to integrate all together into a unique entity. Okay? So why, in theory, what you could do is to actually build a unique model. Well, the first issue is that it would be huge, because one model of this sort of network would be one of the models you've seen, like, for example, throughout this conference, and already those are challenges. But perhaps more critically is the issue that actually no one would own the statements that the model will tell you. And that's because you are in a very heterogeneous domain, you have different contexts, different domains, and actually no one will be the owner of the model. And another very serious issue is that the scientists that build the models, what they usually tend to do is to constantly revise them. So for example, if you have a simulator, what the scientists tend to do is to try to improve the resolution of the simulator. And if you have a unique model that embeds that simulator, you will need to change the whole model. While if you have some sort of network structure, you would only need to change that simulator and the other remain as it was. Okay? So what I claim that what is needed in this sort of domains is an integrating decision support system, what I call an IDSS. What this does is that it selects probabilistic outputs from each of the contributing submodels and then combine this appropriately according to some rules. So briefly, an application where we have observed this sort of problem is nuclear emergency management. So just a brief history. In 1986, there was this Chernobyl accident. The Russians were sort of keeping everything secret, and the response in Europe to the accident was really conflicting. Each country was doing something different. Political parties were all saying different things. The public was really confused. So what sort of the scientific community decided to do afterwards in order to prevent from this sort of confusion was to build a decision support system, which was called RODOS, from a collaboration of different research institutes in Europe, and by responding to a potential emergency using this decision support system, you would have sort of a coherent response across Europe. Okay? Now, if you think of a nuclear emergency, how does that unfold? You have like a source term, a chimney, you have a release of contamination. This contamination then is dispersed into the environment. It might deposit on the ground, into water, and then you have like human absorption, animal absorption, And all these different things are actually related to sort of a different domain of expertise. And what happens is that each of these domains have their own model. So for example, that is a Bayesian network that describes how the plant work. There is a screenshot actually of Rhodos, where you have like the dispersal of air of contamination. And how actually this was built was by having different group of experts collaborating on each of these components and then trying to merge this into a unique model and give response to this sort of emergency management. Okay? So this is an example of why we are looking at these sort of problems. But this was the 90s, and there were many issues with that. First of all, actually, not all the components of that network were probabilistic at the time. And this was because actually having a probabilistic system was computationally very expensive, and people were really reluctant in actually doing these sort of things in a probabilistic way. But the main issue actually is that even if all the components were probabilistic, there is no actually theory on saying like how you would combine these sort of models. And if you were able to combine them, under which conditions the combination would be coherent in sort of a Bayesian way or a probabilistic way. So what happened in Rhodos is that each of the modules, each of the components would compute averages in some way, and then these averages were transmitted according to some sort of message passing algorithm between the components. So all the uncertainty that potentially was actually computed by the components was just discarded, and the means were transmitted between the models, okay? And what does this lead to is like, as we know, if actually your decision making depends on those uncertainty measures, then you're just potentially doing decisions that are non-optimal in a Bayesian sense, okay? So I'll just now give you a little bit of a notation. You have a decision space, which are like the actions that you might potentially do, and you have the group of experts. You have M panel of experts, GI, who are responsible for a random vector YI. Okay, so GI would have built, for example, a model for YI, which is a subset of the overall random vector. Okay, so for example, a node of that network. And I suppose that I work in a parametric setting. Each panel is responsible for a parameter, theta I, and I will assume that the parameter spaces are variational independence. That means that I have a product space of the spaces. And I would simply call the sample summaries and the panel beliefs this quantity pi I and pi theta I. And in a full Bayesian sort of, if I'm in a full Bayesian setting, this will be sample distribution and priors. But for the purpose of decision making, this will actually be just some summaries, maybe some moments or some medians or whatever is required. Okay? And I will assume this is just sort of, for simplicity, that there is a super Bayesian. So each panel of experts delivers some beliefs, and the super Bayesian is responsible to actually merging these beliefs together. Okay? Now, what is helpful to build? It's a common knowledge structure. Okay? So what I will assume is that the experts together as a whole will be able to agree on some structure of the overall model. And usually these tend to be done in practice via decision conferencing. That means that the experts meet in a room for around 2 days, and they come up with a model that represents their whole beliefs. Okay? And this common knowledge class will consist of 3 elements: a set of decision rules, a class of utility functions, and more or less a dependent structure of the random vector Y. Okay? And if you think of this has no probabilistic actually elicitation. This is all a qualitative structure. They will just assume that they have some sort of preferential structure. They have maybe a conditional independent structure over Y, and that they know what decisions they have available to them, okay? And in the literature, it has been argued that it's actually sort of simpler to come to an agreement about qualitative stuff more than probabilistic numbers or other quantities. And this common knowledge class will be everything that is needed to actually perform inference, because then the numbers can just plug in, as we will see. What we need to do now is to actually define some set of properties that will describe when a common knowledge class is actually helpful or is describing the problem in a Bayesian way which is coherent, okay? So first of all, I will be able to compute the expected utility function, which is everything that is needed for decision making, if the beliefs of the panel that the panels deliver are sufficient to compute it, okay? So if you are able to know what your expected utility function will be, then you know what sort of summaries you need the panels to deliver, okay? So this adequacy condition is actually often met in practice, because the probabilistic models can deliver whatever summary you want, and so if you know what these summaries are, you can request them, okay? But actually, in this sort of multi-agent domain, what you need is that the beliefs that the different panels deliver do not contradict each other, okay? And this is what I call a soundness requirement. And this is sort of the most critical part. And I will say that the integrating decision support system is distributed if actually the beliefs of the super-Bayesian are a function of the panels of the beliefs of the panels. And this entails computational speed, because then actually whenever the panels deliver their beliefs, it's a simple function of these beliefs. These beliefs of the panels can be computed in a very difficult probabilistic model, but once you have them, it's very fast to collate them together, okay? So this is a very simple example, but it tries to show you where things can go wrong. So suppose you have two binary independent random variables. Each are under the jurisdiction of two different panels, and you have two different utility functions. One is a linear combination, and one is there's a product term. So if your common knowledge class includes the belief that actually your utility function is a linear combination, then in order to compute your expected utility, you just need each panel to deliver their prior, okay, mu I. But if actually the preferential structure of the group is in the U2 class, then if you just compute the product of the prior means, you don't have adequacy anymore, because those two beliefs are not sufficient for compute actually the expected utility function, okay? But if actually then you add that independence condition on the prior parameters, you retrieve adequacy, okay? This is very simple, but as soon as the model becomes bigger, you can see that, but it may become tricky to actually understand what's going on. And here is an example of learning. So suppose you have a random sample x1, x2, and each panel just is random samples, so GI will see xi, G2 will see x2. So if I have prior independence on the parameter, then each can perform Bayesian updating separately, and they can deliver their posterior means, and just everything will be adequate again, okay? But if actually I don't have that independence condition between θ1 and θ2, what happens is that dependence between θ2 and θ1 induces a dependence between θ2 and x1, okay? So if the super-Bayesian had the possibility of seeing all the data, they would use a posterior mean which is different from the one that the panel would actually deliver. So in this case, the overall model is not sound anymore, okay? So now I will just try introduce 4 assumptions, and what I will show you in the next slide is that these 4 assumptions are able to guarantee soundness. So if the common knowledge class embeds this assumption, I can create an IDSS and combine the preferences and the beliefs of the panels in a coherent way. Okay? So first of all, suppose that I have information, which is usually data, which I call JT, but only a subset of that will be admitted. And this is usually done actually even for single agent. If you think of Cochrane in medical meta-analysis, only data which is sufficiently good is admitted. I will call I0 the information that is common knowledge to everybody, and Ij the information that a panel GI would want to use to update theta j, which is the parameter of another panel. Okay? And I just put everything together into I star, the beliefs that each panel would use for their own parameter set, parameter vector. So these are the 4 assumptions. Delegability, what does this mean? Is that the information that is admitted is equal to the common knowledge information and just to the information that each panel would use for their own parameter. So if the panels are working collaboratively, this is what happens if a panel passes information to another panel if that can be useful. Separator inform and cutting basically describe what we mean by an expert. So for example, for cutting, what does this tell you is that no panel beside GI has information that is informative about theta I, okay? And commonly separated is basically a global independence assumption, for example, in a graphical model, okay? Which tells you that given the information that is shared, the parameters are independent. So if you have these 4 information, and if you know that your system is adequate, then it will be sound, and it will be distributed. And basically, what you need to prove is that actually you have that global independence assumption given the whole information in the system, not just the common knowledge, and that given the information that GI would use for its own parameter, any other information is independent of that parameter. So, and to me, it's quite striking that actually you prove this just by using the semi-graphoid axioms. So this is sort of the main result. And I don't have the time here, but basically, this works under any uncertainty reasoning for which the semi-graphoid axioms hold. So you can do it potentially with a belief function or any other reasoning for which the axioms hold. And actually, one thing that we have been doing is extending causal argument, not to work only within each of the models, but the interface between the models. And this is sort of very useful to do. And we have developed new algorithms which allow you to compute the expected utility very fast in these sort of domains. And very, very briefly, one thing that I've been sort of observing is that if you are actually able to build these sort of models where these independence conditions allow you to actually do all the inference or the decision making by just computing, by imposing that the panels deliver some beliefs, and then you collate these beliefs according to some formula. And for example, in the binary case, the formulas were those U1 and U2 bar. In some other example is, for example, that one on top. And in other paper, we have other examples. What you can see is that these are just polynomials. And these polynomials are functions of these beliefs. So if you actually know this polynomial form, then you can just play with this polynomial. And you can plug in different values and see how this change. So this actually turns out to be very fast once you have that. And you can do quite different things. So what you can do is, for example, This is a polynomial that describes an influence diagram, and you program it in Maple, and it gives you this polynomial. Then what you do is just say you can perform different sensitivity analysis by just changing one of the parameters, and you don't have actually to run the models again. And you can sort of study different behaviors of your probability or expected utility function. So just to conclude, what I hope I've been trying to convince you to is that sort of networking models is something that we might need to start looking at. And if you actually do that, you have many advantages. Distributivity, which implies speed of computation, and you can then perform various sensitivity analysis. You can do different stuff. But of course, the 4 assumptions I was discussing are no sort of like regular assumptions. You need to check whether those can hold. But for example, in many single agent applications, those are assumed. And in what we have been showing is that in a multi-agent setting, there is no difference, basically. And very briefly, I've talked about sort of polynomial models. Thank you.
Are there any questions for Manuele?
There is a long tradition of polynomial models, polynomial networks, and this kind of thing. And those models are extremely sensitive to Gibbs phenomenon, to hyperparameterization. What kind of measure can you take to avoid this phenomena?
I don't know which type of models you're referring to, so it's kind of difficult to answer the question. Do you have any example of this or reference to this sort of models?
Some of them went with the name of Penetra. No, don't know it.
Any other questions? Okay, so let's thank Manuele again.